Hello, folks. Long time no see. Sorry about that. I had some good news last month, and I was not able to record videos. But moving forward, I should be able to keep up with the videos, and we're going to be diving into the deep learning now. As promised, we're going to do that, but we're going to be doing this more or less kind of like sequentially in a way. And the reason I'm going to be doing it is not for of course, this is not for getting more views or more subs. That's not my priority right now. The priority is that I want to have these videos in a way that if someone's going to ask me what I'm doing, if I'm, let's suppose, implementing a recommender system or recommendation system, and I'm using dot product with embeddings. If someone's going to ask me, oh, what is this? Why are you doing? What is an embedding? Like, what are you doing? I'm going to be able to link the video and say, oh, that is what I'm doing. Okay, embedding is just it's just a collection of numbers in a way, right? So, and that is the reason I want to have them this way. And today I want to discuss project structure for machine learning, deep learning projects. So modern artificial intelligence projects. And I also want to go over the convolutional neural network, a very simple convolutional neural network for the MNIST classification, okay? Let us dive into the MNIST now. One thing I'm going to say right away is that the project structure that we have right now, it is of course not like one size fits all kind of a structure. It depends on the complexity of the project, and the more complex the project is or becomes, usually it means more directories, okay? Right now the setup is kind of very simple. For maybe some of you who program in the Go programming language, it might be kind of similar, putting everything in the root directory and calling it a day. But again, this is not one size fits all kind of a thing. It depends on a project. And even here, we're going to have at least one directory that is kind of very useful. That's going to store data, data set. And there's going to be another one for models, okay? But again, depends on a project. All right, the first thing I want to show you is that I'm a big fan of reproducibility. That means using tools like virtual environment. Okay, so WandB in Python. You can do that using this kind of program in a way. You're invoking whatever's in Python using M. It's a module called WandB, and you can call it, and then it's going to create directory .WandB for you. And once you have that, you can source WandB bin activate to activate that virtual environment. And then you can actually use pip and Python, and you can do just pip install requirements instead of doing Python m pip install our whatever requirements, okay? Of course, in a general case, if you have multiple Python installations, and if you're not using tools like pyenv, it's recommended you do Python -m so that it's actually, you're installing the packages to the right Python, but here it actually defaults to the Python you have in this virtual environment, so you can just do pip install r requirements.txt. Now I'm not going to run it. We can take a look at the requirements.txt. Have sklearn, so scikit-learn, torch vision, and WandB. We're going to go over that as well. I'm not going to run this because it's going to take some time to pull the dependencies, so torch takes some time, and I already done that, so we don't need to do that. Next step is talking about the model itself. And for those who don't know, MNIST dataset. MNIST dataset is the handwritten digit database. So handwritten digit dataset. So you have digits like this, right? And the goal is to classify them, okay? And that's the dataset. And now I call this MNIST model because we're working with the MNIST dataset. And you can see what I do. I define two convolutional blocks, block 1, block 2, and then I define the multi-layer perceptron. So I have two linear layers and the AdamW activation function in between, right? AdamW, it's the same as the swish activation function. Torch calls it AdamW. And so we do that, and then we just perform the forward pass. And of course, we could have implemented backward on our own if we wanted to, but of course the torch has the built-in automatic differentiation, so we don't need to do that. Now, you can see what I do in the block 1 here. I define what's known as this NN.sequential. It's like it basically allows you to chain these different functions, or in this case, these are more of like classes in a way. And in this case, what we do is that we first do a 2D convolution, then we do what's known as max pooling. We do a 2D max pooling. Again, I didn't make a video about this. It's kind of simple. It's kind of similar to a convolution, except for it's way simpler. So max pooling, I'm going to just explain it through this. Maybe this is a good example. Yeah, you see here, I guess it's 2 by 2 kind of a pooling where the stride is also 2, and so this 2 by 2 matrix is sliding over this image. Again, it's a single channel image, whatever, a grayscale image for the sake of simplicity, but it can be a 2D image with multiple channels like RGB, right? So that does not really matter. But for the simplicity here, a single channel image, we slide with this matrix, and for every kind of matrix or submatrix of this bigger matrix it covers, we're going to take the max value. So in this case, it's 20. Then we move here. We take 30. Then we go down here. We take We take 112, and we go here. We do the max, and we take 37, and we get that. That's pretty much the max pooling. There's no tricks with this. There is also min pooling, and you probably guessed how that works. Instead of doing max, you do min. There's also average pooling. Instead of doing min or max, you're going to say, oh, I'm just going to average out all the cells and take that value. But this is generally how it works. You either take min, max, or average. Of course, you can customize that as well, assign a different kind of weights to different pixels and so forth. But this is generally how it works. I mean, by the picture here, you can see that one of the primary reasons we're using this is dimensionality reduction. So helps with reducing the size of the feature vector, if you will, the size of the representation. And it also speeds up the training because we're not dealing with these large images in this case. And of course, there are other kind of benefits it provides. One of that is that it, because it takes the max values, depending on what kind of problem you're dealing with, it can actually take out the neurons or take out the pixels that, depending again on a problem, might be more important for the problem at hand. Sometimes you do average pooling, sometimes you do max pooling, min pooling. That depends on a problem, depends on the kind of image classification you're doing or the signal classification you're doing, because again, max pooling, convolution, these are general kind of signal ML kind of tools, not only for images basically. After that, we do batch normalization. Okay, batch normalization, maybe I'm going to make a separate video about this, but this is very helpful for dealing with what's known as the internal covariate shift. And I'm not going to go over that right now, but there are several reasons why this is useful. Number one, it kind of helps with overfitting in a way. It's kind of like a regularizer. The way batch normalization works, let me actually show the formula. Batch normalization, impl. Well, maybe I have it. Well, let me see. Okay, this implementation right here. Without the scale and shift, if we take a look at this right here, so we take the value, we subtract the mean, and we divide by the standard deviation, pretty much. Well, of course, we have parameters like epsilon, but you can think of it that way. And one of the things that normalization in general does, and in this case batch normalization, is that it kind of introduces noise in the system, right? You're like subtracting mean, dividing by like a standard deviation. In this case, we have some epsilon there too, so maybe more noise. And so adding noise, of course, what that helps with is reducing variance, right? That's pretty much how the regularization works, right? And so, well, L2 regularization and the elastic net regression. That's the way they work, right? And so, batch norm helps with that, and it also helps with internal covariate shift. I'm not going to talk about it right now. I'm going to make a separate video about it. CILU, again, that's an activation function. And so we have one block, then we have another block, and then we need the multi-layer perceptron. The reason we need that is because in the end, we have 10 classes with MNIST dataset, and using MLP, it's just one way to get the this kind of 10 output of size 10. There is actually a way to take the linear layer and convert that into a convolutional conv 2D layer, the convolutional layer. But I'm not going to go into that right now. Maybe you can look it up yourself. One of the benefits of that would be that it would reduce the number of parameters, because with linear layers, the number of parameters you add is usually 1600 times 32 and so forth. And so you can have this kind of it can blow up with these numbers, with the number of parameters here. Okay, and then we do forward. What forward does is that we go through the first convolutional block. It's convolution, max pooling, batch normalization, swish or CILU. The second block, then we do the MLP on the flattened version. We have to flatten it because that's the way linear layer works, and then we output it. Now, notice that I'm not using like a softmax or anything right here. The reason I'm not doing it is because I have in the training code, I have the where is it? Cross entropy loss right here, and it by default uses a log softmax. I believe that's what it uses. And so this is a very handy activation function. We could have done it manually, like use maybe nn.softmax here, or log softmax. But the cross entropy loss, it helps with numerical stability, and it basically, in some cases, even speeds up the training. So super helpful. Other than that, what we do here with the setup is, I'm going to comment this out for now. Use deterministic algorithms. Let's suppose we're not doing it. And I'm going to go over that as well later on. We first define, I like separating basically these arguments. And we define this parse args functions. And what that does is that it parses command line arguments. Okay. What that means is that now I can use this function here, and I can pretty much have these, well, let's not train, have these arguments here, right? So I have batch size, I have whether to shuffle the data set, the shuffle parameter, or the argument. I have number of workers, the number of workers, worker threads, basically the learning rate, weight decay, epochs, the model directory, as well as the model name. Next, what I do is that I use this tool, WandB. That's how it reads, WandB. It stands for weights and biases. And this is the website for it. It's wandb.ai. And this is my profile, David Oniani. And right now I have one project here, MNIST. It doesn't have any runs because we have not run the project yet. Before we're going to run this, let us go over what this does. We parse the arguments. We initialize WandB, okay? And actually, before doing that, you do have to do like WandB login, and you provide your API key, whatever you have, right? It can be whatever, letters, numbers, and so forth. And you have to do it. I am logged in, so I don't need to do that right now. So we need to do this. We need to initialize. Once you log in the CLI environment here, or the using this TUI, the terminal user interface, then you're going to be able to initialize the WandB. Next, we define data loader, and you see that it's just MNIST. The reason for that is because MNIST is actually built into PyTorch, and I made use of that fact, basically, define a function, and I pull this data set straight from the torchvision.datasets. And then I use some, functions. I compose a number of functions that look like classes. They're classes actually, but I do a composition of normalization and conversion to a tensor and so forth. But that's basically just the data set. The interesting part starts here. Okay, we define the MNIST model. Okay, this is the model that we import right here. Right, we define it. It's right here. Then we do NN.data parallel to make it to enable parallelism basically, and we enable the train mode, the training mode basically. Data parallel and model train it already kind of enables CUDA, and I don't really have a very powerful CUDA here, powerful GPU, but it's still okay for MNIST. It has around 4 gigs. Next, we define the criterion, so the loss function. We use the cross entropy loss. That's for the classification, followed by the optimizer. We use weighted Adam. And the reason we're using weighted Adam, I can recommend reading this. I'll recommend reading this paper called, I call it Fix Adam, but it's decoupled weight decay regularization. So initial Adam paper, it had some problems with the way it was implemented in Torch and in general. And so at least the implementation had problems. And this paper, Fix Adam, as I call it, goes through these issues. I'm not going to go through that right now, but I recommend you read that. Next, we define the optimizer, right, with learning rate and weight decay that we have from here, right? And we have some default values, so we don't necessarily need to provide every single parameter in the command line. And then we perform a traditional kind of training, some number of epochs. We have this running loss so that we can log it. We iterate over the data set. We zero out the parameter gradients. Well, we get the data. We zero out the parameter gradients. We do the forward pass. We do the back propagation, the backward pass, and we then optimize. And finally, every 375 steps, we log both on the in the terminal as well as in the WandB. Now, it's probably better to use logging here, although I think print is also fine in this case. Then we create the directory for storing models, and we do it with this kind of check. If it does not exist, create it. And then we save the model. Okay. We also save the parameters, and I do JSON dump with indent4. The reason I put indent4 is because it automatically formats the parameters as well, so that's nice. Okay. All right. So now that we know how this works, let's train it. All right. Okay. We're logged in. It automatically downloads the data set. janlekun.com, goes and downloads the MNIST, and it starts the training. The reason I picked 375 is because for the training set, we can divide it by 375. It does not have any. It does not have any. It has a remainder of 0. Basically, it divides perfectly. So yeah, let's see. It should be, I think, in total 4 epochs. And yeah, it's divisible by 375. Okay, so we start with 0 because that's how we do it in computer science. Let's see. Okay. Waiting for WandB process to finish. Success. That's cool. And it generated some, terminal plots. Okay. Of course, we're not going to rely on these, but kind of nice, summary. Loss decreased from 0.176 to 0.024. Okay. And let's take a look at the structure here. What has changed? Well, we have the data set now. To take a look at the data set, let's do tree. Data set, MNIST, raw, and we have some, the gzip or the gunzip files, and then, or is it the gz files? And then we have the unzipped version of these. we have the model. Okay, so the model itself, and I like the singular names for these directories. Dataset, model. I do not really like the plural versions like models and datasets, so I use that. So we have model itself, and we have the parameters. Now, in the training code, you can see that we save the, where is it? Right here. We save the parameters here as well. The way we do it is that we use this vars to extract out like the dictionary of these parameters. And it turns out the dictionary of these arguments or parameters is that's exactly what we have here. It's like batch size, 32 shuffle, true. Basically the values we set by default. And we have saved the model as well. And we also have this WandB directory, okay? We have debug internals log. We have some, config YAML. We can look into that as well. Latest run, logs, debug log. We have whatever TMP. We don't have much there. Config YAML. Oh, it has a lot more information actually. Start time, Python version, is Kaggle kernel, is Jupyter run, framework, torch, and here are some of our, not some, but all of our parameters, I think. Yeah. It does not really have description. I could have added those as well, but it's kind of simple. The way we've implemented this, we don't need to specify much. Where is it? No, not eval, but the training. We just do the vars. Okay, now that we trained this, it's time to evaluate the model. But before that, let us take a look at what WandB did. Okay, so I have this project. Let's refresh it. Okay, now it has 1 runs. Okay, let's click that. All right. Okay, so you can see we have the epochs. Of course, it went up because, that's the epoch numbers. The more we train, the more epochs we're going to go through. We have the number of steps. Comes down, goes up, comes down. Makes sense. We have the loss. Goes down. We also have things like, GPU power usage. We have system CPU utilization per core. How cool is that? Okay, and I'm not really, advertising for this, or I'm not shilling for the company. I'm just saying, very cool product, right? So, and one more benefit of this is that maybe I'm training my model, not maybe, that's usually how it goes. I SSH into a server, and that's where the real training goes, not on my laptop, right? And so I want to monitor how my model is doing, right? Of course, it's going to be very difficult to do it using like a phone, right? I could have installed like some custom OS on my phone, and then, maybe not custom, but I would install maybe Linux, and it's possible to do SSH and so forth, but it's a lot of pain. Instead, I can log into WandB, into my account, and monitor what's going on live. I can go to this website, right? So super cool. Okay. Now let's evaluate this. Okay, let's see. Eval.py should be running. Okay, we have accuracy, precision, recall, and F-score. They're the same, but I believe this is a balanced data set. That's a part of the reason why that is the case. But pretty good result. 99.1% accuracy, precision, recall, F-score. Everything is good here. So yeah, that's basically set up for a simple kind of model, in this case MNIST. And of course, if, just like I said in the beginning of the video, if the project was more complex, we would have more directories. It's likely that we would. So instead of having one dataset pi, maybe we're going to have several dataset.pis, like MNIST.py, CIFAR10.py, although I don't really like that dataset, or some other custom datasets, right? So Vision.py that downloads maybe some datasets from Google Cloud or AWS, or so that can change. With .venv, we can go out of this or deactivate it, and we're no longer inside the virtual environment, but we can again reactivate it using the source .venv bin activate. Okay, So one more thing now I want to show you is reproducibility. If you want to be completely reproducible, if you want your work to be completely reproducible, there is this thing called torch use deterministic algorithms. And I put some info about this in the README as well. You should set the environment variable cuBLAS workspace config according to your CUDA documentation, and you can visit this page. Let's see. Well, it's very slowly. Did they update their website? It seems like they did. Okay. The cuBLAS library. Let me see. cuBLAS. Right here. And so that's basically depends on your system. In my case, I just set this, right? So I just set to that, and if we comment this out, this is important that we have torch that use deterministic algorithms true. If we train this, it's not going to re-download the data set because we have that downloaded. It's going to see that that's the case. Okay, it's going to run. Now I'm not going to, well, I don't really want to go through the entire training process. I'm going to stop here. But you can see the first 4 values right here. I'm going to maybe copy them here, okay? Let's do it again and compare the values. You're going to see they are the same pretty much. I don't want to go over the entire, training right now. Training loop. Okay. Epoch 0, epoch 0, epoch 0. And you can see the values are the same. So this is like a fully reproducible kind of setup where every algorithm, whatever we use, is deterministic. Let me see. So let's call this B, A. Well, in B we have one more. So now diff A and B, they're the same. Okay, I'm going to remove A and B. And yeah. So this is what I wanted to show you today. Use virtual environments. Actually, it would be even better in some cases to use Docker. Okay, for full reproducibility. Sometimes, maybe not in this case, in this specific case, but it would probably be better if you provided Docker container. In this case, I'm not saying it's absolutely necessary because the MNIST model is just so widespread and everyone uses it for different benchmarks and so forth, that maybe that's not super important. But actually, I would argue that maybe even here it's important. Maybe I should have done it. Maybe I'm going to add it to the repository. But yeah, reproducibility, very important. I've read a bunch of papers where, not only read, but implemented where my results were a lot different from their results. And the reason for that is because even when they share the code base, okay, a lot of times they don't, but even when they share the code base, it doesn't have, you don't know what version of TensorFlow or Torch or PyTorch, I guess, they're using. You don't know versions, you don't know what they are using at all. You have to go in and, think about whatever, functions and methods they're using. Are they available right now? If they're not, when they were, what was the point in time they were removed? And so you have to think about that. So super important that everything is reproducible. You may not be able to do it, for every project, but whenever possible, please make it so that the code base or the results are reproducible, or reproducible as much as possible. Okay, so that means having requirements.txt file. That means, if it's possible, Docker container. Super cool. That means also having a directory structure that makes sense. That helps a lot when you're reading code, when there are directories that make sense, when you don't have like random directories like whatever new in Windows, I believe there's like new folder. I've seen those on GitHub too. It's like, okay, like what is going on? And as I mentioned, if it improves readability, if it improves the maintenance or long-term kind of maintenance, helps with that. Helps with maintenance. Please create more directories, right? If it makes sense. Do not create hundreds of directories or tens of directories. if it's not necessary, right? Keep it minimal, keep it straightforward, but make it so that it makes sense, it's readable, and if someone else goes in and reads your code, they can see, oh, okay, that's train.py. Okay, that makes sense. It's probably for training. Model.py, what is it? Well, that's probably for model. The model itself. Model directory. Okay, could be model, could be models. I prefer singular, as I said, over plural. What is it? Well, it's probably models, and you can see the extension. It's model. Dataset directory. What is it? Well, again, it's the dataset, right? Dataset.py. What does it do? Well, it has dataset in it, so it has to do something with the dataset. And indeed, all it does is that it just downloads the dataset and does some transformations on image data. Okay, so yeah, thanks a lot for tuning in, and I'm going to see you next time.